All right, so the regen drive, the R6. To start things out, have you guys had experience working with these? I know that they're starting to become more and more popular, especially with the use of permanent magnets. So for the most part, the R6 is going to be the standard KEB solution regen drive out there. There's going to be two different variations of the R6. We'll talk about both types in the presentation here. I'll also go through just kind of from an application standpoint, which ones make sense for regen, which ones don't, where you'd want to use it. So just kind of going through the basic operation, how the regen actually works. With electric motors and generators, ultimately they work the same, but just in reverse. With the elevator application, we're using a counterweight. Because of that, for roughly half of the time, the motor will act as a generator. So in an empty car up situation or a full load down situation, the motor will actually act as a generator. The nice thing with power and electric motors, power can go both ways. It can either be put into the system or taken out. And depending upon if you're using a permanent magnet motor, we can actually do that quite efficiently. All right, so a few things that are going to affect regen. The first component, we're going to talk about potential energy. So this is going to be energy due to gravity, so how high something is. If we take apart that equation here, we've got mass times gravity times height. Okay, gravity is going to be the same no matter where you are on Earth. So mass and height are going to be your biggest factors in determining the amount of potential energy you have. Obviously, the higher your building, the higher capacity car you have, you're going to increase the amount of potential energy available in the system. All right, the next kind of energy, we've got kinetic energy. This is energy due to motion or inertia. If we look at this equation, we've got half times the mass times the velocity squared. All right, so if you're not using a regen system, you would be dumping that extra DC bus voltage over a braking resistor during overhauling application. That's going to be located in that intermediate circuit of the VFD. And in this situation, we only have power going one way. So we're feeding power into the system. Anything excess is being dissipated across that resistor. Ultimately, that's just going to turn into heat. If we add a regen unit, now we actually have the opportunity to go both ways with power. The regen unit is going to contain much of the same components as a drive. It's going to have input rectifiers. It's going to have a DC bus capacitor bank, so much like the drives. So regen operation, how does this thing work? What is it doing? It's measuring the line frequency, and ultimately when the DC bus level gets above a certain level, 103% of the idle DC bus, it's going to start regenning or putting energy back on to the line. As soon as that DC bus level falls below that 103% threshold, it's going to stop regenning. Power is going to flow back the other way. You're going to start consuming power from the line. This turns on and off by itself. There's no inputs that you have to program into the drive for regen operation. This is all done by the regen itself. Some things to look at with the braking resistors. What do? They're going to cause an extra amount of heat, especially if you're in a bank of several cars in a smaller machine room. In the summertime, it's probably pretty hot. So hot that you may actually have to install an AC unit and run that. Ultimately, that's going to lead to higher energy costs there. If you're using a regen, you're not going to have that extra heat generation. You're going to save on some energy there, and then you're going to put energy back onto the line, so you're going to use less. So you kind of have two parts there of where you're actually going to save energy. A few things that are going to affect the efficiency of the system itself. Anything that's going to limit the amount of regen power, so things like gearboxes, shaftway efficiencies, the actual efficiency of the motor itself. Ultimately, there is no such thing as a 100% efficiency. We're not going to be able to get exactly everything that we put into the system back out due to those losses. But the more efficient system we have, the closer we can get to what we put in getting back out. So why would you want to put one of these in other than the economical benefit of saving money? Well, you get to say that you're saving energy and that you're green. Exactly. That seems to be the name of the game going forward here. A lot of people are interested in the LEED certification. This may play a part in that. All right, so some things affecting the payback. So we've got the mass of the rated load. So that is in both the potential energy component and the kinetic energy component. We also have the speed. That's only going to be in the kinetic energy. And then system efficiencies. Some of these systems are going to be just inherently more efficient. So obviously your permanent magnet motors are going to be more efficient than your induction geared ones due to that elimination of the gearbox. Roping ratio, that's another one. 1-to-1 versus 2-to-1. 1-to-1 is going to be better. We don't have that extra sheave or extra pulley that we're going through there. Again, that's an area that you can lose some efficiency. All right, so we're going to do a quick cost analysis. We've got 3 different applications of will it work for this application? So the number one, we're going to look at PM gearless applications. Which ones work well there? High speed, high efficiency geared applications. Can I use it there? And then the low speed geared. All right, so the first one, the PM AC gearless. Which ones should be considered? Right off the bat, anything from 200 feet per minute up to 1,400 feet per minute, absolutely. It should be considered. The potential for payback is good here. So here are some examples where this would be used. 500 foot per minute hospital cars. Hospital cars have a lot of traffic. Those are great candidates. Mid to high rise condominiums or buildings. Again, you've got that height benefit of the potential energy component. Passenger cars in general, yes. And then 1-to-1 cars rather than 2-to-1. 200 to 350 foot per minute MRLs, yep, they work there as well. So bottom line, PMAC gearless, 200 foot per minute or above, chances are it's a good application. All right, what about geared machines? Yes, you can, but really we're going to talk about higher speed and higher efficiency. We say anywhere from 250 to 450 foot per minute worm gear or a helical bevel gear. Gearing here is gonna really influence what the amount of energy you're gonna get back here, as well as speed. Your 350 foot per minute, 2,500 pound passenger car with a worm in a mid-rise. That's gonna be a good candidate. We can go a little bit slower with the same capacity with a helical machine in a mid-rise or even a low-rise. That's due to the helical gearing being more efficient than a worm gear. Worm gear is actually pretty inefficient. And then 250 foot per minute or above freight cars. So again, we're going to have a higher mass capacity here, and that's where we can make up for that with the slower speeds. All right, so applications where that aren't suitable, they're not good candidates. That's going to be anything 200 foot per minute and below. Ultimately, you're just not going to get your payback there. Usually in these applications, the motors are going to have a lower efficiency. Even though we say that these aren't good applications, it seems like they're getting installed no matter what. Again, it's coming down to the green label. Everybody wants to say that they're green, that they're saving energy, so even from an economical standpoint, if you're not going to get your payback, they still are installing them. So here's an example analysis that we did. We do have a calculator available online that you can go in and punch in all of this information, and it'll give you a cost estimate, how many years it would take to pay back, what kind of money you're going to save, how much energy you're going to save. It's only going to be as good as the information you provide. So if you only want to provide a few different sets of information, well, ultimately your estimate isn't going to be that accurate. But I get calls, all the time saying, hey, what's regen? How much money am I going to save? And I'll ask, well, okay, what's the capacity of your car? How high is the building? What's the time or the distance between the floors? And they don't know that. They just want, well, I'm going to save, X amount of dollars a year. Ultimately, if you want a good estimate, you're going to have a lot of information. So here are some valuable pieces that we're looking at. So in this situation, we're looking at a 500 foot per minute, 5,000 pound car. Few things here. The counterweight, we're at 42%. Efficiency of the gearbox, it's a gearless machine, so 100% since there is none. Shaft weight efficiency, we've estimated at 88%. And then if we move further down here, this is the how busy the car is. So we're wondering what the peak period looks like, how many calls per hour, how long the peak period is. That's going to affect obviously how much energy you can put back. If we go over to the right side of the screen here, we've got some D-cell times, XL times, what we're looking at, run time. Here's some assumptions that we made. So an energy run, we'll say 13.7 kilowatt hours. Energy during D-cell is 13.6. Energy cost, we've estimated at 14 cents a kilowatt hour. And then how often it's going to be run, 365 days a year, that's pretty accurate. So in this example here, if we just look at the energy, what we can save on pure energy costs, it's going to be about $1,400. So that's per year. So from an energy perspective, that's decent. Another area where we're going to save, we're not going to have to cool the machine room, or we're not going to have to cool it as much. So we can say we're going to save about another $1,000 there. So total, about $2,400 a year. Now, if you look at how long this is going to take to make a return, 2.5, 3 years. I think anybody will tell you if they can get their money back in that time frame, that's a relatively good investment. So, in this application, it's a good candidate. All right, so we kind of went through some good candidates for regen. What kind of money you can expect to save, how much energy you can save. Next, we're going to move into the troubleshooting and adjustment. All right, so with the R6, we've got two versions. We've got the R6N and we've got the R6S. They are virtually the same unit. The only difference between the two is going to be the control card. The S is going to require this Cat5 cable that connects the sync module on top of the choke to the unit. The sync module is where the frequency is going to be calculated for the line. So that needs to be connected to the R6S. The R6N has an updated processor on the control card. It's much more powerful, it's much more robust, so we can eliminate that sync cable. We don't need a sync module on the choke. We will still need a choke, but there's no need for that cable anymore. I'm going to focus on the S unit first. Just a few things to note about that. We have two wiring schemes that are available. We refer to them as wiring scheme A and wiring scheme B. The R6S can be in either wiring scheme. The R6N, however, can only be in wiring scheme A. Just a note going forward. Wiring scheme A. It's used where the regen is used for supply power for the F5 elevator drive. We've got three-phase power going into the regen, and the drive and the regen are connected via the DC bus here, the plus and minus. Notice it's not connected to the braking transistor, it's directly connected to the DC bus. Wiring scheme B, we have three-phase power going to the F5 drive. We also have three-phase power going to the regen, and we have this line contactor here, along with an extra set of fuses. Now, looking at the difference between these two, does anybody have an idea of why you would want to use wiring scheme B versus wiring scheme A? What's unique about wiring scheme A that wiring scheme B doesn't feature? It's got an extra set of fuses, it's got the line contactor. But if you notice, in wiring scheme A, all power that comes into the drive here has got to come through the regen. So what does that mean? Since we don't have three-phase power coming in here, that means all power that comes into the drive and ultimately goes to the motor is running through the regen unit. Likewise, same happens in reverse. Anything that's going back to the line, all has to go through the R6 unit. If you look at wiring scheme B, where we have three-phase going to the drive, The only thing that's going through the regen is power that's going back to the line. It's not acting as the supply in this case. So what that means is it comes down to a sizing consideration. There are some applications that will require 2 R6 units in parallel to supply one of these drives. That's due to just the amount of current that's going to be drawn. So you would require 2, where in wiring scheme B, you could get away with just 1 unit, just because the power is only going one way. But again, if you're in wiring scheme B, you've got this extra line contactor, and you've got an extra set of fuses, and you're also wiring it back to the line. So it's kind of a cost to benefit analysis of whether it pays to if you're really going to save that much more by not installing 1 unit. So parallel units, yes, you can put the regens in parallel. Actually, you can put 3 of them together if you wish. If you do have an application where you're putting 3 regens together, we recommend upgrading to our larger size regen. It's a size 25R housing. It's much larger, and that way you're saving on controller cabinet space, less wiring, and instead of going from 3 units, you only have 1 unit. The thing with parallel operation is just setting it up correctly. We have a master-slave configuration setting. We can't have 2 masters. We can't have 2 slaves, master and a slave. Also, too, with the regens, we do have 2 keypads. The difference here is that the keypad for the regen is going to act as a straight user interface. There's no parameter storage on the keypad itself. All the parameters are going to be on the regen. The keypad is just really used to make parameter adjustments and to view your diagnostic parameters. So we do have 2 versions. The one with the older style, which is similar to the older style keypad that we have with the red letter display, and then the newer one, which actually uses the keypad that some of you have in front of you with the SD card slot in it. That's what's used on the newer style. All right, so a parameter overview, what's available to look at. Again, there's not much to set here. Mostly it's just diagnostics. CP1 is going to be the status display. That's going to indicate if you are in a regen operation or if you are in a standby configuration. Standby just means that the unit is enabled, but it's not actually modulating back to the line. CP2 is going to be the mainline frequency. This needs to be positive, and it needs to read 60 hertz. If it's reading a negative 60 hertz or 0, that means you have a phasing problem at the choke. So to fix that, all you would do is switch 2 phases at the choke. CP9 is going to be the DC bus voltage. Since the regen and the drive are going to be connected via the DC bus, they should have approximately the same DC bus voltage level. There will be a slight difference between the 2, but they should be sitting at around the same level. CP19 is going to be the DC bus switching level. This is only going to be available for the R6S. I'll talk a little bit more about that later. And then CP21 to CP28 is going to be your fault log. So all the faults that occurred, they're going to be stored here. The thing with the R6 and fault logging is that if the same fault occurs one after another, if you get, say, 2 overcurrents in a row, only CP21 is going to say EOC. CP22 isn't going to say EOC either. That's just the way it was designed. Multiple faults that happen, if they're the same and if they happen in a row, are not going to be logged and pushed down. So that can be problematic when trying to troubleshoot, because you're wondering, what fault did I get? When did it occur? A way around that is to force an external fault to create a bookmark. What that would do is basically just log an E.EF into CP21. Since you know that you did that, any new faults should appear in CP21. And the way you do that, I'll talk about that as well, but you're just going to jumper two terminals on the terminal strip. Some parameters that you would need to adjust. CP19 for the R6S. Yes, this is one you may need to adjust. What CP19 does, just go back to this wiring diagram real quick. So this contactor here, during power up, we're going to have to charge the DC buses. Now, we have a potential problem if the R6 is connected to the main line as well as the F5. Because when we turn on power, the DC bus of the F5 is going to charge. The DC bus here is going to charge from the line, but it's also going to charge from the DC bus of the drive since they're connected. So because it's going to be charging from two different ends, we've got the potential to cause damage to the unit. So we put this line contactor in so that during the charge up phase, this line contactor is open so that the DC bus charges from the DC bus of the F5. That way we're not trying to charge from the line and from the drive at the same time. As soon as the DC bus reaches the CP19 level, this contactor will close and then it'll be connected to the main line. Some potential issues with that where it's going to cause some problems is going to be if your main line is starting to sag. If your main line sags enough, that contactor may be pulling in and out and causing some operational issues on the regen. CP34 is going to be the control angle. This is another adjustable parameter. This is basically going to adjust the phase angle at which the AC sine wave is being put back onto the line from the regen. Why you would want to adjust this is noise. So the R6S is going to be a much louder unit than the R6N. It's pretty apparent if you have them side by side. The R6N doesn't make much noise at all. The R6S, it'll sound like a buzzing sound coming from the regen. Sometimes that buzzing is so severe that you want to try to mitigate it a little bit. Try adjusting CP34. Usually decreasing that will help a little bit. If you look here, the green is going to be your AC sine wave from the line, and then the pink is going to be what the regen is putting back onto the line. So that CP34, what that's going to do is it's going to shift this pink curve either right or left to that green curve here. The area underneath this curve is going to be the power that you can put back to the line. So if we start shifting this pink curve over to the right or to the left, we're going to decrease the amount of power that we can actually put back, the amount of energy that we can put back to the line. So that's why you may have a little bit of noise benefit, so it might be a little bit quieter, but ultimately you're going to reduce the amount of energy you can put back onto the line because you're shifting this pink curve over. And if you notice this pink curve, it looks like a square wave here. That's due to the pulse width modulation, PWM. It's not going to be a perfect sine wave. This is what's going to be similar that's going out to the motor. It's going to resemble that's kind of square wave. All right, CP33, your operating mode. So that's where you would set your master and your slave configuration. If you're using a harmonic filter, that's also where you would set that. Then CP35 is going to be the input logic, PNP, NPN. CP20 is going to be the auto reset counter. It's going to be the amount of times that the regen will automatically reset a fault until it requires a manual hard reset. CP21 to 28, that's talking about the fault log. Again, we need to create that bookmark, the E.EF for an external fault in order to know what fault is happening most recently. That can be done by jumpering X2A, pins 15 and 17 together. And all you need to do is just hold the jumper there for a second or two. You'll hear a little click, and then you can take the jumper off. Another note on the regen, since the keypad is not doing any processing, it's simply acting as a user interface, you can operate the regens without a keypad. Keypad does not need to be on the drive, or excuse me, on the regen. On the drive, however, the keypad needs to be on. And also you cannot put a regen keypad onto a F5 drive, and you can't take a drive keypad, put it on a regen. So the turn on procedure, you're going to turn power on. R6 is going to calculate where the idle DC bus voltage is at. It'll say, okay, I'm going to add 3% to that. That's where I'm going to start regenning back to the line. It's going to look at the frequency to make sure it's at 60 hertz. Because we are putting energy back onto the line, line side issues are going to be that much more of an issue. Power quality is going to be an issue. Any EMI disturbances that we might see, if you're going to have problems with it, it's likely going to show up on a regen. That just has to do with the fact we're putting power back onto the line. We need to know exactly what angle to put that sine wave back on. So it needs to be perfect so that we're not going to damage something else in the building. Unfortunately, though, with that, it's going to be much more sensitive to noise. So if you've got any grounding issues, they would likely show up in a regen application. Here's a couple of errors that you would see. NOP just means no operation. That means that the unit is not enabled. It's just sitting idle. Standby, that means that the regen is enabled, but it's not actually putting energy back onto the line. Regeneration is active. ENET means error, missing line phase. It's going to be 7 cycles of a sine wave is going to be the threshold at which the ENET kicks in. It'll either kick in if you're missing all 3 phases or if you're missing only 1 phase for 7 cycles or more. EFNet means there's an error in the line frequency, so it could be out of tolerance. This happens, the EFNet error happens a lot during generator operation. A lot of times power coming from a generator, it's a lot dirtier. You might have some frequency issues there. The EOL, error overload, means that you drew too much current for too long a time. And you've reached the overload threshold in the drive. ESYN, that's that line frequency synchronization. If your phasing is wrong, you'll get an ESYN error. Yes. So the question was, the EOL, which direction is it going to be active for? It could be both. So it could be drawing too much, could be putting too much. Because ultimately it's going through the same transistors. It's going through the same portions. So the levels might be slightly different. If you look at our manual, we actually will have different levels for what the input versus the output. Ultimately, when we size things, we're going to size it on what's coming in. We're going to size it off of input power. So we look at the input overload ratings. EUP, under voltage, means your DC bus is too low. E.EF is the external fault. That's whatever you want it to be, or if you want to reset the fault log. And then the EOC is the error overcurrent. Again, that's going to happen for a ground fault or a short. EOC, ENET, EFNet errors. Some common things here. If you're going to use a regen, whether you use an isolation transformer or the building transformer itself, needs to be in a center grounded Y configuration. If it is not, if it is in a unbalanced delta configuration, the noise suppression of the regen is going to be voided, and you're going to have operational issues. You're going to get the EOC, ENET, or EFNet. So anytime you are seeing these errors, one of the first questions that we're going to ask is, are you using an isolation transformer? And how is it wired up? Is it in the center grounded Y configuration? That's going to come down to that XO or X0 terminal being grounded. You might see an ESYN or an EFNet right when you boot up. If the error clears itself, that's fine. If the error doesn't and it remains, then yes, you've got a frequency issue. If it's still reading 0 and you've done all the switching on the line phases at the choke, it could actually be the choke itself or the sync module. So that is one thing you can change. All right, so that concludes the R6S. Now we're going to move on to the R6N. All right, so the R6N, again, it's going to be the exact same unit. The only difference is the control card. We've upgraded the processor on it. It's got a much more processing capability. We're able to get rid of this sync cable that goes to the choke. It's going to automatically calculate the frequency, automatically calculate the degree, the phase angle degree that it's going to put the AC sine voltage back onto the line. In some applications that were susceptible to noise with the R6S, as far as EMI disturbances, that type of thing. We've actually replaced them with R6Ns, and problems have gone away. So we've seen situations where we're getting intermittent EOC, intermittent ENet errors, intermittent EFnet errors. Ultimately, we've concluded that it's due to noise of some sort. We've installed an R6N, and it's taking care of the issue. So it is a much more robust solution. Some of the advantages, the biggest one is going to be the sound. It's very, very quiet. You're going to have a constant buzzing sound from the R6S that's been eliminated in the end. You're going to get a little bit better harmonic performance, around 45% total harmonic distortion. You don't need the sync module that sits on top of the choke. You're going to have a slight cost savings there, and then no wire to run either. The parameter structure going to be the same as the R6S. Where it's going to be slightly different is going to be towards the bottom here. CP19, since we can't use the R6N in wiring scheme B, it's not going to be a factor, so we can't adjust that. But down here, CP34, so the R6N is automatically going to calculate the control angle. We don't need to set that, so we replace that with input type. That's where you're going to select if you're using a harmonic filter, if you're using a commutation choke, and the master and slave configuration. And then also, we added some harmonic filter gains. If you're using a harmonic filter, these are adjustable, but for the most part, the default values work well. That concludes the R6. Does anybody have any questions on regen? How it works? Which applications work well?